So this shows, like for the pin we were talking about, pin 1.2, if there's a 0 in the corresponding bit 2 position in the port 1 selection 1 register and a 0 in the bit 2 position of the port 1 selection 0 register, then it's used for general purpose I/O. On the other hand, if those two bits contain a 0 and 1 respectively, it's functioning as either a transmit or receive pin. You see, in most cases, with 2 bits, we can select 4 different functions, right? 2 bits, we can count the 4 different things. Most of the pins only have 2 functions. There are actually only a few that have 4 possible functions. So for these set of pins, the selection 1 and selection 0 bits should only be 0, 0, or 0, 1. And you shouldn't have them 1, 0 or 1, 1. But then down here for the 4 function pins, you've got all possibilities to select the possible. These are actually the ADC, analog to digital conversion channels. Okay, so how do you set the pins? So a particular selection register So X here can be any one of the 10 ports. Okay. So 1 through 10, and PX selection 0. And then each one of these registers is an 8-bit register. So PX 7, PX.0, PX.7. So each one of these pins, P1.2, we have to set the port 1 selection 0 and selection 1 registers. We have to set 2 bits in that for P1.2 to have it general purpose I/O. We need to make sure that the second bit, so this is 0, 1, 2, we need to make sure the second bit is 0 here and 0 here. If we want to have it the serial receive function, we need to make sure that we've got a 0 in bit 2 here and a 1 in bit 2 in this particular register. Okay, does that make sense? You have to do that for all possible. So this particular microcontroller doesn't require that all pins in a port have the same function. Okay, individually, they could be general purpose I/O or an alternate function. So let's look at a particular example in some detail. So to choose the UART function on pins 6, so I'll write this way. It's port 9, pin 6, and port 9, pin 7. We need to set corresponding bits cell 1 is equal to 0, and selection 0 needs to be equal to 1. Okay, so that's actually, I think, on the next. Let's see, port 9, 6. You see, that's for one of the other UARTs. We want to set these 6 and 7 up for their serial interface function. So that means we want to set the corresponding bits in the selection 1 register for that port to 0 and the selection 0 register to 1. So what I recommend that you do is typically I'm going to start out, okay, this is what I need to do. I need to make sure that P9 selection 1 and P9 selection 0 in bits 7 and 6. I need zeros there, and I need ones there in those particular registers. And ideally, when you do this, you want to affect only those 2 bits in these registers, right? You don't want to change the functions of the other registers. An easy way to do this is essentially to actually write a 0 to that particular register address, a binary 0, and set the whole thing to 0. But then that's going to change the function of the other pins. So especially in a long program, you know, some of the pins may be assigned different functions, and you don't want to change the function. We only want to set those bits to 0 in the selection 1 register, and these 2 bits to 1 in the selection 0 register. So one way to do that would be in C is P9 is actually defined in this header file with its particular address. So we don't actually have to dig through the manual and find out what the register address is for this P9 register. But it's a pointer to a structure, actually. And what we want to do, again, we'll look at this in a lot more detail. You can find the corresponding address. We can find the definition of that structure. But we want to actually set, what we can do is and this with OX3F, right? Clear B6 and B7. Because OX3F and binary would be 0, 0, 1, 1, 1, 1, 1, 1. So what does this do? This reads the current value that's in that register, P9 selection 1 register, ANDs it with 3F, which means if we AND with 1, it doesn't change the contents. But if we AND with 0, it will clear those respective bits. So what is this going to do? It's going to set those 2 bits in that register, regardless of what they currently are. They both may be zeros, they both may be 1s, they could be a 1 and a 0. It's going to read that value and AND it with 3F. So that would set those 2 corresponding bits to 0, and then we write it back to the register without changing any of the other values. Now, how do we set bits to 1? We just OR with 1, right? That won't change. That will change any value to a 1. 1 ORed with 1 is 1, 0 ORed with 1 is 1. But if we OR the other bits with 0, that won't change the values. So generally, if you want to set a value, set a particular bit value, you're going to OR with 1. If you want to clear a particular bit value, you're going to AND with 0. So those are the 2 operations. So the other thing that we need to do, P9 selection 0 ORed with, and here we want 1, 1, 0, 0, and those upper 4 bits, 1, 1, 0, 0, that's 12, 8 plus 4, or C. And then the lower 4 bits, we want to be all zeros as well. So we want to OR with O hex C0. That will set B6 and B7. More importantly, it doesn't change any of the other bits. We read the current value, OR, and then write that value back. Now, what you'll see in the book, and this is shorter notation, is you can do it like this, and equal, it's that compound operation, but it means read the value or this value with, now here, I'm going to do 0xC0, because 0x3f is the bit complement of 0xC0. Now, why do it that way? It's exactly the same as the line above. Okay, this saves me some typing. Okay, this is shorthand notation for equal and. But why write C0 instead of 3f? Well, I want to think about the bits I'm changing. It's only bit 7 and bit 6, and if I think about only those 2 bits and everything else being 0, then that would correspond to C0. And so by doing it this way, you know, I'm not having to write this out and say, well, you know, this I need ones, everyone else here. I can think about only the 2 bits I'm interested in. And similarly, the other one, or equal OXC0. That's the other reason. I see the same 2 values here, so I can be pretty sure that I'm affecting the same 2 bits. Now, if I needed to, you know, clear the bits in the selection 0 register, I would AND with, again, the not here. Or if I wanted to set them, you know, again, OR with the value I get from those 2 bits. Any questions about that? Yes, no?
That tilde sign.
That means a binary not. So yeah, so this would take the 1, 1, and followed by 6 zeros and convert to 0, 0 followed by 6 ones, which is what 3f is. So not C0 is exactly the same as just writing 3f. You can certainly do it this way, but doing it this way, I don't have to worry about computing the one value corresponding to the 2 bits that I want to change. Okay, so, and we'll be doing, so this is the first step. Okay. Set the function of the pen, okay, that you're going to use. And by default, most of them are in the general purpose IO state already. So we don't really have to change the purpose if that's what we're using them for. It's not bad practice to go ahead and set them anyway appropriately in some initialization portion of your code, you know, before you get into the loop. Okay. So we're not only using this microcontroller. These pictures are all in your book. I tried to, I've frozen this thing somehow. These pictures are all in your book. I tried to scan them with my phone, and I don't have enough hands to do that very well. But this is a picture of the board we're using, this Launchpad evaluation board. This is the little microcontroller here. It's got a whole nother section of the board that's got this debugger chip on it that also provides the USB interface. That's where we plug in our USB cable. It's got a reset button on it. Okay, and then there are these jumpers that actually connect the 2 halves of the board. You can actually use this thing for development with the debugger. You can actually break the board in half once you're done with your debugging, and actually use this portion for, you know, your production microcontroller or whatever. Okay, so, but there's a lot of features in this evaluation board that we're using. The most important one is it has the microcontroller on it. 401R. And there are different versions of this particular ARM chip. ARM is a very popular processor. They've got different versions of the ARM processor. But this is, so ARM is an open source hardware, so anyone can download the designs of the microcontroller and build your own ARM processors. So this is from Texas Instruments. So this is the TI microcontroller. And then it's got a debugger chip that's on the other half of the board. Okay, here's your microcontroller, and then this debugger chip is the big integrated circuit that's on the other part of the board. It's got this USB interface for debugging and for serial communication. The debugger that we use with Code Composer Studio can actually connect directly with this debugger chip, and we can examine register values within the microcontroller itself and see exactly what's happening. On some systems, and instead of using an onboard debugger like this, you have to debug your program using a simulator. So it's not the actual hardware, but a computer program that simulates the actual hardware. Those typically aren't as accurate as debugging on the actual hardware, which is what this interface allows us to do. There's the one reset switch. So you've all found that. There's two user switches. So again, they threw a little extras on this few extras on this evaluation board that you don't have to use these. We'll use them, especially since we're learning how to program. It's convenient to have these two switches already available. Switch 1 and switch 2, they're directly connected to port pins. So we can use them to play around with the board without having to connect our own little push button switches. We do have additional switches in our parts kit that will interface to the board, but there's some that are already built on the board for us. There's one tricolor LED and one red LED. And so I'll talk in just a minute about these other connectors. Okay, these connectors are through printed circuit board traces are connected to these pins on our microcontroller. Okay, but fortunately we don't have to try to attach wires directly to the pins on the microcontroller. That would be really tough. Instead, we'll connect wires to these connectors to get access to those pins. But in order to use those switches, or even turn the LEDs on, you have to know what port pins they're connected to, right? So again, this is a diagram out of the book. And so, for example, if we wanted to turn on, this is the red LED, this is the tricolor LED, but if we wanted to turn on the red LED, we'd have to set pin 1, bit 0 on port 1 rather, pin 0 on port 1, the general purpose I/O function. Again, that's the default. And then we have to write a binary 1 to that particular pin. I haven't showed you how to do that yet. Okay, I've only showed you how to actually select the function. But in order to write a logic 1 there, we just write a 1 to another address, much like we set up the selection registers. Okay. That will turn the LED on. And I'll write a 0 to that bit in a particular register, and that'll turn it off. And you see, we also have, if you want to turn on the blue LED, that's pin 2 on port 2. We'd write a 1 there. The switches are connected to 2 pins in port 1. Pins 1 and 4 in port 1. So we can directly read those switches on those two ports. If you notice, all of these are actually on your board, you have these various jumpers. Okay, so you can remove these jumpers which connect two pins. So it's essentially creating an open circuit. So if you remove this jumper 11, which is down here at the bottom of the board next to that red LED, I'm sorry, next to the blue LED, you're going to break this connection between that port pin and this blue LED. Why would you want to do that? Well, maybe you want to use that port pin for some other purpose. It also comes out to one of these connectors. So you want to drive something else with it and disconnect it from this. You know, these are things that are on the board really just for us to play around with. But if you want to use these port pins for something else, you can. Notice that there's no jumper to disconnect the switches. The switches are disconnected as long as you don't press them. So you could use those for something else as well. There are also 4 port pins that are used for the serial interface, this USB serial interface to the debugger chip. And you can disconnect those jumpers. Those are the jumpers that go between the 2 halves of the board. So if you wanted to break the board in half, don't do that. We're going to be using this board all semester. We'll be using the serial interface. You could remove those corresponding jumpers. Again, if you wanted to use these port pins for something other than their serial interface purpose. But right now, leave all the jumpers for the entire semester. Leave all the jumpers in place. We've got plenty of other port pins to play around with that we'll never have to actually remove these. If you do, then you won't be able to turn these LEDs on or off. Just going back. So, and you can see on your board, there are these 4 10-pin connectors on the sides here. I think they're labeled J1 through J4. These together, and you can access them either through the pins on the top, or they've got connectors on the bottom that you can just insert wires into to access those. And these are all tied, and if your eyes are much better than mine, you can read which particular port pins on the microcontroller these are tied to. So, you know, on the right-hand side, with the USB interface at the top, on the right-hand connector, the one in the upper left-hand corner says P2.2, right? You see that? I think I'm seeing that correctly. So this one right here. Yeah. Does that say P2.2? 2.7. Okay. I told you my eyes aren't any good. So P2.7. But that would be bit 7 on port 2. We could make a connection to that. You know, if we wanted to either connect a switch up to it or an LED or anything else, a motor, a solenoid. So, of course, you have to know the mapping, not only the hardware mapping, but you know, you can't just arbitrarily connect the device up to a pin without knowing what pin you're mapping to, because you've got to drive that pin in software. So you have to keep track of where you have your devices connected to. These 4 10-pin connectors can be used together to attach what are known to this particular board as booster packs. I don't know if any of you have actually used the Arduino microcontroller, but the Arduinos have a similar connector that you can plug in Arduino. I don't think they call them booster packs, like Arduino headers or something like that. So one of the things you can do is actually get another board that plugs right on top of this, for example, that has an Ethernet controller on it, so that you can do networking with it. There is no Ethernet controller on this particular board, but you can buy another one, just put it right down on top, and give it Ethernet capability. And then there's another connector down at the bottom. I think it's 38 additional pins at the bottom. I think that's connector J5. That brings out some of the other pins that are available on this microcontroller. So we've set up the functionality. How do we actually read and write data to a pin? Well, let's talk about that. So again, it's a couple of steps that are involved. First step is making sure that we've got our selection bits in our selection registers set or cleared appropriately. The next thing we do is we write to a port direction DIR register to set pins as input or output. So through the use of the selection registers, we've designated various pins as being I/O pins as opposed to analog to digital converter or serial interface pins. But once we've done that, we still have to choose whether we want to be able to write to that pin to turn an LED on or off, or be able to read from that pin, like reading in from a switch. Now, we only need to set one bit for that, and that's done through this direction register. You know, with a 0 there, I think it's an input. With a 1, it's used. We can write values to that. So if, again, this is an 8-bit register. Every bit in it corresponds to one of the pins. We'll have one 8-bit register for each port. Each bit in this register corresponds to one of our pins. The Dura 0 pin is an input pin. And this is in the next figure. Now, don't confuse reading and writing to the direction register or reading and writing from the selection register as reading and writing to the pin. Because it's different. This is actually setting up the function. That's just showing the connectors. This came out a little crooked. So we have to write, what was the example, I guess? Well, there we set them up differently. But we have to write to the direction register. And we have to write a 0 if we want to use that corresponding pin as an input pin. And that means input to the microcontroller. So this is where we would hook up like a switch, for example. Okay. And you can ignore all of this because it's used for the output function. But so if you write a 0 to that bit in the P9 direction register, that and it's set up for general purpose I/O, that means, you know, whatever bit this is, let's say it's bit 3. So P9 bit 3. P9 bit 3, we've set it up as an input pin. We have to read from the corresponding input register. It was off my board. Read from the input register to actually read the switch value. So you have to configure it for input, read from the in register. Again, each port will have a corresponding input register. We'd have to read from the P9 input register, just like this, except it would be PN, P9, and then an arrow in instead of the selection register. to read that corresponding bit value. And then we can see if it's a 1 or 0. Okay. Any questions there? So we read from the port input register to read input values. And then the final thing is, and this looks a lot more complicated than maybe it is, if the bit is 1, pen is an output pen. Again, typically you're not going to, you would set these up initially. This typically isn't changing while your program is run. You set up a particular pen as general purpose input output or its alternate function, and then you would set it up as either an input or an output pen. To make it an output pen, you write a 1 to that particular bit in the direction register. Then now, just like to read from that pen, we read from the input register. To write to it, we write to the output register. So you would set that 1 bit, again, typically by ORing the output register, because we only want to affect that 1 bit, ORing that corresponding bit with a 1 to set it high, and then clearing that bit, ending it with a 0 to set it low. And then that would actually set that corresponding pen to a low or high. And on our board, which uses positive logic, if we set it high, we're going to turn those LEDs on, for example. Okay. Now, there's some other capability on the output ports on this particular microcontroller. It has what's known as readable output ports, which sounds strange, but once it's set up for output, if you want to, you can read from that output port to find out what was the previous value you wrote to that output port. Okay, so once you write to the output port, it's latched in this D flip-flop. And then so you write that value, it's stored there. And then as long as this pen is high, it's output to the pen. But we can actually read the latch value by reading from that output register. Again, I don't think this wouldn't be a common operation, but it's essentially like reading and writing from memory. These flip-flops are essentially memory. You could use it as an additional byte of memory, I guess, but we could read from that value that's been previously written there. Or you can read directly from the output pen. If we're driving this high, we can read that by reading from the input register. Okay, so again, it's got some extended capability that I don't think we'll probably won't take advantage of that. We'll primarily just be reading from an input pen, like on the previous slide, and then writing to an output pen. So we'll talk more about this next time, and then actually get into some code where you should be able to turn some LEDs on and off on our boards next time. It's just a few lines of C code or corresponding assembly.
All right. So for project 2 for 310, you just want like the files, or you want like a screenshot of the outputs?
Yeah, if you could just put it all into like a Word document, so cut and paste your code into just one file. So like a Word document, cut and paste your code into that, and then capture the screenshots of the figures.
Okay.
That'd be great.
Do that after.